M.Manukrishna, roll number E21B02, sir. Now I'm going to explain our digital signal processing project. The topic of our project is active noise cancellation. Why noise cancellation is essential in our lives? Let's start with what is noise. Any undesirable sound that can disrupt signals is termed as noise. They are mainly of four categories: continuous, intermittent, impulsive, and low frequency noises. Noises can have different side effects. Some are useful, as shown in this slide, while the majority are harmful, as can be seen in this slide. The various harmful effects include health, economic, and environmental damages. Now, to tackle these harmful effects, we need to achieve noise cancellation. So what is noise cancellation? It is a method of reducing the ambient noise or unwanted sounds by the addition of a second sound that specifically cancels the first sound. They are generally of three categories: passive, active, and adaptive noise cancellation. Passive noise cancellation. It is also called as noise isolation. It revolves around the idea that there has to be a physical barrier that dampens the noise entering your ears. Active noise cancellation. The first noise that is detected from our immediate environment by a microphone that is located outside our headphones is then analyzed by a machine and broken into several readable parts that are called as sound waves. Now, the sound antiphase of the sound wave, that is of equal magnitude but opposite shape, is fed back into our headphones to cancel the ambient noise. Finally, adaptive noise cancellation. It is similar to active noise cancellation in the sense that negative noise is added to cancel the positive noise in a noisy environment. The difference between adaptive noise cancellation and active noise cancellation is that it uses advanced algorithms to produce near perfect noise cancellation to best match the environment. Now my teammate Chirag will take over.
Hello everyone, I am Chirag Kotian, E21B025, and I am here to explain you what all we have done. So let's first begin with what is our aim. Our aim in this project is to achieve adaptive noise cancellation for varying passive noise attenuation. And also we'll try to implement this in such a way that the entire system is properly hardware implementable. So as you can see, this is the system we are assuming that will be present in our hardware. There is a multimedia device which will be giving a sound signal which will be going to our DSP, which is digital signal processor. Digital signal processor has 4 ports. One is the input to which we give our sound signal. Then there are three more ports: output, feedback, and noise. Noise is an port which has been fed through the noise microphone. This noise microphone is outside of the casing of the speaker. This will measure the ambient noise in the surrounding. Next, inside there is a speaker whose input is connected to the output of the DSP. This will be our main sound producer. Beside to that speaker, there is one more mic which will act as a feedback device. So it will measure the signal, it will measure the sound produced by the speaker alongside the noises which are able to pass through the foam barrier, which helps us in passive noise cancellation in general headphones, and it will give it to the DSP. Let's move forward. So let's see how did we design and implement our ANC model. For doing this, we have used a software called as Simulink, which is a Matlab based graphical programming environment for modeling, simulating and analyzing multi-domain dynamical systems. The major benefit of using Simulink is the availability of many mathematical tools there and also analytical tools which we can use to see how our system behaves, and also it's easier to work with it and it can mimic our real life system. So let's see what are all the noises, input signals and the noise plus input signals which we have used in our project. This is the noise signal. Now let's see the input signal, which is the song. Now let's see how, when noise is superimposed with this song, how does it hear? As you can see, it's not very clear and it is very difficult for us to analyze what is going on. Our song, which is the main thing which we want to hear, couldn't be heard clearly by us. So let's try to remove this noise. Let's first begin with workflow, like how did we implement the entire system? We first began with extracting data from the signal and plotting the signal, whose subsystem you can see here. Then we went forward with generating the inverse of the signal. Then we started to see the results of like how the original noise plus sound, and also how the inverted signal when superimposed, what are the effects we get, what are the effects when we superimpose the noise and its inverted signal. When we superimpose noise and inverted signal, as you can see, we get a flat line because the noise and the inverted signal cancel each other. Whereas we can see here that these two graphs show how superposition of noise and signal and also noise and signal inversion are look in a spectrum. Then we generated the did the superposition of noise plus signal and the inverted signal, considering that the passive noise attenuation is fixed. That is, we know the passive noise attenuation, as you can see here. Then we went on to implement the adaptive noise cancellation, where the passive the gain of the inverted signal is automatically detected by the algorithm and it adjusts it according to the passive noise attenuation. This is our Simulink model. As you can see in the first model, it represents the diagram which I had shown you before. Here is a DSP. Then here we can see like how here is the noise input and here is the song input. We have used the model itself to generate song plus noise, which you can see from here, and also the output and the noise plus song signal we can see here. This is the internals of the subsystem DSP, that is digital signal processor, which we have made. Let's talk more about the complete system. As we can see, the block which I have covered in red shows the parts which are responsible for generating the passively attenuated noise and the original song superposition. So this is what you will hear if we don't have any active noise cancellation in the headphones. The part which I have circled here shows the outputs outputs after superposition and also their respective signals. This part shows the how feedback loop comes to the DSP, and it helps us in and it helps the DSP to calculate the gain. Now let's dive deeply into the DSP, that is digital signal processor. So this is the entire digital signal processor system. Let's first begin with the first section. This section deals with digitization of the noise signal and inverting it. We use the property of signals that the multiplication of signals in time domain is nothing but convolution of the same signals in the frequency domain. We use that property here to generate the inversion of the signal. In the below block, you can see this is for the gain calculation using feedback. The feedback which we obtain from the microphone, which is beside the speaker, is fed into the digital signal processor, and this gain control logic unit has some algorithm running in it. It takes in this feedback, takes in the power of the feedback which we have calculated using the RMS block and the power of the song itself. Then it compares it, that is, it subtracts both the powers and sees how much the error is. The lesser the error, the more closer the signals are. That error is fed into the gain control logic. The gain control logic sees that error, and if it is above a certain threshold, it keeps on increasing our gain, which we can see through these displays here. As you can see from the output, we have one more branch which is given back to the system for the incrementation of the gain. But there is some delay here. I will get back to the reason why we have added the delay in the later part. Now next, let's move on to how we are superposing the signal gain. So here what we are doing is the gain which we get from the gain control block is fed into the product block where it is multiplied with the output of the inverted noise signal. So using this, we are controlling the amplitude of the inverted noise signal. Then we are superposing this with the original song. Next, here that the superimposed signal, which is currently in the digital format, is converted to the discrete time domain format using IFFT and taking the real value of the IFFT, which we can feed to our speaker, which due to the inertia of its diaphragm converts this discrete time domain signal to a continuous time domain signal. Now let's see what is the algorithm behind gain control logic. In gain control logic, we have set one required error, which is the error we desire. So what we do here is, if our error which we get is greater than our required error, we keep on increasing the gain in steps of 0.005. And once it reaches the required error, we don't change the gain. Now let's see some outputs. As you can see, I have set one random value of the passive noise attenuation in the gain block given here. As you can see here, the current noise cancellation gain which we are getting is very close to what we had set initially in the passive noise attenuation gain block, which is here it is 0.68, there it was 0.7, which proves that our system, even though it didn't knew what was the passive noise gain attenuation, has automatically adjusted itself using the closed loop feedback to reach to that noise cancellation gain. Now let's see some frequency domain analysis. See the spectrums of the frequency in the frequency domain and see how our output is differing from the input. Here we have four spectrums, as you can see. The first spectrum shows us the clean audio. That is the audio which we obtain after the noise cancellation algorithm has worked on it. Initially, it won't be resembling the original song, but as our gain reaches to the proper values, it will more and more resemble to the original song. Here we will see how our noise spectrum is. Here we will see what will be our output if there was no active noise cancellation. Here we will see original song spectrum. As we can see, the original song which we have here very closely matches to the clean audio signal here. This shows us that the algorithm which we have developed for the active noise cancellation is working very nicely here. So what are the features of our system? The features of our system is the entire system is designed in such a way that it can be easily implemented with minimal components using digital processor and other electrical components like multipliers, adders, etc. The system adapts noise cancellation gains automatically regardless of the passive noise attenuation due to physical isolation of the ear from the speaker using materials like foam. This has been achieved using a closed loop feedback. As it as we have seen, regardless of the passive noise attenuation, our system automatically sets its gain in such a way that it is always trying to reduce the error, and the final gains are very close to the original passive noise attenuation gain. Here I would like to point out some assumptions which we made while making this system. We have assumed that the time it takes for the DSP to calculate all these gains and all these things is equal to or smaller than the time it takes for the sound for the noise to reach from the noise microphone to the feedback microphone. Also, if the time processing time is lesser than the time it takes the sound to travel from noise microphone to the feedback microphone, we can just add a delay block based on our processing times. Now I will tell you the limitations of our model. So, as I had said earlier, we had a delay block between the output and the old gain in the gain logic control. So why is that? That is because the in Matlab, when we have such loops, it is known as algebraic loops. Those loops are solved by Matlab using some prediction algorithms, and also it is an iterative process. So when our error becomes smaller and smaller, it becomes difficult for the Matlab's algorithm to calculate the proper values. Hence, our simulation breaks. So what we saw was when we added the delay block, that is, we are not giving the direct feed through feedback. We are helping that algorithm to stabilize and detect proper values. Even then, the algorithm which Matlab uses fails when our error values are very small. Also, you can, as you had seen in the delay block, the delay there was given of 4 samples, which we had found after trial and error method that the delay of -4 works the best. Next limitation, which is the limitation of our system, I want to point out is that the nature of our logic which we have written is that the gain constantly increases. And if in case due to some reasons our passive noise attenuation of the system changes, then our system cannot react to it properly. It needs to be restarted. Thank you for listening to our presentation. I hope you like our presentation.